Greetings, beautiful people. Welcome back to Find XYZ, where we think, find, and shine. If you are new to this channel, kindly subscribe, like, and leave a comment. Let's grow the channel together. In today's episode, we are discussing properties of binary operations. Let's look at this scenario. Let's pick a set of football players. So we can have player A, player B, player C, and so on. Now, we are going to perform an operation on this set of football players, and the operation is passing. Now, these players are going to pass the ball among each other. So let's select two players, player A and player B. Now, the operation is passing. So if they pass the ball among each other, then we can say that the set is closed under the operation of passing. So it's closed under the operation of passing. However, if the ball lands outside to this soccer fan, clearly the soccer fan is not a football player. He's not part of the set. Because the ball has landed from one player to the soccer fan, we can say that in this situation, the set is not closed under the operation of passing. So if the ball is passed between players, because players are part of the set, it is closed. However, if the ball lands outside of the set and gets to a soccer fan who is not part of the set, we can say that it is not closed under the operation of passing. So the property that we are going to discuss today is called closure property. Let's define the property. A binary operation delta is closed under a set A if for all x and y which are elements of A, the operation of x and y is also in A. So what does this mean? This means that we are discussing about a set and an operation, such that whatever element we pick in a set and perform an operation, the outcome must be from the given set. If it is outside, then we say it is not closed under the operation. So we need two things. We need a set and an operation. Why is this useful? This is very useful because imagine you have a machine where the machine can take only certain inputs. It means that there are certain things that the machine can accept. If the machine ends up producing something which is foreign, it means that the machine is going to jam and then the machine is not going to work. So it means that for reliability and for stability and for consistency, we need to show that operators that we are working with can give us something which we know, something which is not new to us, so that we can work on them. We don't want any foreigners. We don't want any outsiders that we don't know. Okay, so let's take some examples. Let's pick a set of even numbers and then let's use the operation of addition. Now select any two even numbers. So I am going to select 4 and 8. Now what is the operation? The operation is addition. So I can do 4 plus 8 and that will give me 12. The question is the outcome. Is it part of the set that we are working with? Yes, 12 is an even number. Hence, we can say that the set of even number is closed under the operation of addition. Now, this is what I want you to do. I want you to, on your own, pick any two numbers and perform the operation of addition to verify whether the set will be closed under all even numbers. You can try a lot of examples and then you leave your answers in the comment section. Let's try another activity. Let's pick a set of natural numbers. Then the operation, let's use subtraction this time. The set of natural numbers, we have 1, 2, 3, 4, and so on. Now let's pick any of these numbers. We are selecting 2 because we are dealing with binary. Focus on 2 elements at a time. So I'll do 3 and 5. Now let's do 3 minus 5 because the operation is subtraction. We are going to arrive at -2. Now you ask yourself, this output, this outcome, does it belong to the set of natural numbers? Yes or no? A big no. Because this element does not belong to the set of natural numbers, we can conclude that the set of natural numbers is not closed under what? The operation of subtraction. It is not closed under subtraction. So if you are working on a set, let's assume that you have blue objects, you are combining them, definitely your output will be a blue object. However, if you get something which is not blue, it means that it is not known in the set. Hence, it is not closed. Okay? So a goat gives birth to a goat. But if it happens that a goat doesn't give birth to a goat, then we can say that it is not closed. So it is like a natural phenomenon, right? Let's try another example. The given example is an operation is defined on a set S, 0, 2, 3, and 4. And the rule is P plus Q minus 2PQ. We are asked to determine whether or not the set X is closed under the given operation. Because we have been given a finite set, we need to construct our table using the elements within the set. Take note, you cannot use anything that is not included in the set. So we are only going to use the elements that has been provided. That is 0, 2, 3, and 4. And then we are going to use the operator here. So let's complete the table. So we are going to do row by column. So we'll do 0, 2, 3, 4, and then 0, 2, 3, 4. Mind you, you can only use the element within the given set. So this will be the row and then a column. So we are going to do row and column using the rule. So I am going to fill it. Take your time and do it on your own. Pick the pair of points, 0, operation 0. Then you do it to verify my answers. Is that okay? So let me complete the table. I have successfully completed the table. So the next task is to determine whether or not the set is closed. How can we do this? We can do this by observing the outcomes. If we find any intruder, it means that the set is not closed. Is there any intruder in this section? 2 is part of the set. 3 is part of the set, 4 is part of the set. However, -4, -7, -10, negative, all these elements are foreigners, are intruders, are outsiders. We do not know them. Hence, the set is not closed under the given operation. So let's write the statement. Since -4, -7, -10, -12, -17, and -24 does not belong to set S, then set S is not closed under the operation. So you just need at least one element that does not belong to the set. So once you get that element, then you can conclude that the set is not closed under the operation. Let's try our last example. In this example, the given operation star is defined on a set M, 1, 3, 5, 7 by the rule x plus y all on 2. The first task, draw the table for star on the set M and to determine whether or not operation star is closed under M. Let's complete the table. Take note, you can only use the elements within the given set. When you are completing the table, for any pair of points, you are going to use the rule. So this is for x, this is for y. So we can do 1 plus 1, that will give us 2. 2 divided by 2 give us 1. I'm going to complete it. Take your time to verify my findings. I have successfully completed the table. I hope you also did. That means you are done with the first part. Let's move on to the second part, where we are asked to determine whether or not the operation star is closed under the set M. What do we need to show? We need to look at the outcomes. Then we have to identify whether or not there are elements that are not in the set. Now, do we have foreigners? Do we have intruders? I can see 1 here. 2 is a foreigner. We don't need him. He's not part of our set. I have 4. It's a foreigner. We don't need him. It's not part of our set. And 6, we don't need him. He's not part of our set. So let's draw a conclusion. So based on the premise or based on the observation, we can conclude that 2, 4, and 6 are not part of set M. Then we can say that since they are not part, set M is not closed under the operation star. So we just need a premise. We just need elements that are not in set, and we'll base on that premise to draw our conclusion. Thank you for joining me in today's section. Kindly subscribe, leave a comment, share the video to all your friends, and see you in the next video. I'm out.